Welcome back. This is the day the Lord's made. Let us rejoice and be glad in it. In this video, I'm going to talk about net ionic reactions from a DC chemistry class. So a net ionic reaction is the idea of talking about all the ions that are participating in a reaction and actually seeing what changes. Who actually changed? We've talked about this before. So again, something changes if they change charge or if they change state of matter. So if an ion goes from being an ion and they become more charged or less charged, they would be participating. If an ion goes from being aqueous to being a solid, they have participated in the actual reaction. So there are spectators and there are those that are actually part of the reaction. Spectators are things that don't change. So if an ion does not change during the course of the reaction, they would be considered a spectator. So we're going to look at a couple sample questions to talk about this. So let's say we had potassium chloride, an aqueous solution, mixed with a lead nitrate solution. We could write down the molecular equation. The molecular equation is just basically saying, let's write down the chemical formulas for the things we're adding together. So potassium chloride, here's potassium chloride. Lead 2 nitrate, here's lead 2 nitrate. So the molecular equation is we're mixing these guys together, we're putting out their actual chemical formulas, and then if you're unsure of what's going to happen, do a double displacement reaction. So, okay, we're going to mix these guys together. Let's let these guys mix it up with the group and see if they like anybody. And so we're going to take the positive here, the K, and mix it with the NO3 over here, because again, positives like the negatives. And so this positive was not hanging out the Cl to begin with. They were there, but they had separated. And so then we're going to mix the Cl, who is the first one here, with the lead. So we're going to do a double displacement reaction, put those guys together, and here's what we get. Now you'll see I've already figured out if a solid is generated, so by using my solubility chart. So to do net ionic reactions, you want to have a solubility chart handy so you can actually determine if somebody changed state of matter. So when the K and the NO3 come in contact, rule number 1 says NO3 is always soluble. So what does that mean? That means NO3, he sees the K, but he doesn't stick to him. So he sees his friend at the place, but he says he just waves and doesn't actually go and talk to the person. That's what's happening here. The PB and the Cl, rule number 3 on the solubility chart says what? Cl really likes PB. So again, I have a chart down here for us. Rule number 3 says most halogens tend to be soluble, but lead is an exception. Again, what does this mean? This means that if PB and Cl come in contact with each other, they're going to make a solid. So the molecular equation is just, let's write it out. Let's take our reactants, put them in, do a double displacement reaction, put them on the product side. It won't always be a double displacement reaction, but for the most part, it is in this class. There'll be some acid-base reactions which are a bit different, and there'll be also some reactions where like one metal just reacts with another metal and takes our electrons. And we have some samples here, or let's just say this one sample. The complete ionic equation, this is if we asked for like, put everything in ion phase, everything as an ion. So K and Cl, we're going to actually take those guys and make them an ion, like they would be. If you take these guys into water, K would lose his electron to the Cl, and the Cl would gain the electron. So actually, when you have a potassium chloride solution, what it really looks like is we have positive K floating around and negative Cl floating around. And this lead nitrate solution is actually leads floating around their charge and nitrates with their charge. And then on the right side, we're going to do the same thing. We see the K is still aqueous, so we're going to give him a charge, what he's supposed to have, and put him aqueous. The NO3 is aqueous. The PbCl2, it's a solid. Therefore, we're not going to put it as an ion, even though they are ions. They're actually sticking together. They're now a compound that's found each other, and they're going to stay together. So to find the net reaction, what actually happened, we'll cancel out things that are on both sides. So there's Ks on the left side, there are Ks on the right side that are both aqueous. So the K was a spectator. He didn't change. We have Cls. They did something. We had Cl. They start off as aqueous. Now with the solid, they did something. Pb was aqueous. Now it's a solid. It did something. NO3, aqueous. Aqueous still at the end. NO3 did nothing. So what we actually net, what actually ends up happening is what's left over. 2 Cls run into the Pb, and we get the solid. So the molecular equation is writing everything out in the chemical form. The ionic equation is just putting everything into ion form, and the net ionic equation is canceling stuff out and seeing what actually changed. can you change if you change state of matter or if you change charge? Another example for us here. What if you mix magnesium hydroxide with hydrochloric acid? So our molecular equation would be magnesium hydroxide with the hydrochloric acid. What's going to happen when you take an acid and a base and mix them together? Well, the H likes the OH. So what's going to happen? The H is going to come into contact with the OH and make water. And what's left is whatever the ions are, so the magnesium and the chlorine. So like last time, to write it out the complete equation, we would say, okay, well, magnesium with the hydroxide, since I wrote aqueous, means that they're separated. Actually, there's magnesium ions floating around, hydroxide ions floating around, and they're separated. Again, aqueous hydrochloric acid, even though it's covalent, you should recognize that it is a strong acid. What does it mean to be a strong acid? It fully ionizes. So when we say hydrochloric acid, aqueous, we mean hydrogen ions that are separated from the chlorine ions. All right. Over here, water as a liquid. That is not something that's ionic. Okay, water is a covalent substance. It's not ionized. All right. So we have a change here. The hydrogen here and the hydroxide are coming together to make this. So magnesium hasn't changed. The chlorine hasn't changed. So the chlorine's a spectator. So again, if we see magnesium on both sides, cancels out. We see that the chlorine's on both sides, cancels out. What do we have left over? The acid-base reaction results in H's and OH's coming together, making water. That'd be my net equation. A couple more examples here for us. If we mix potassium oxalate, an aqueous solution with calcium chloride, what would be the molecular, the ionic, and the net ionic equation? The molecular equation, we're just writing the name, potassium oxalate, calcium chloride, double displacement reaction to find out what we're going to produce. We're going to take the first thing and mix it with the last thing. We're going to take the positive from this with the negative of that one, and we're going to take the negative on the first one and mix it with the positive on the other one. And then we'll consult our solubility chart to see if anything happens. We see that these guys here would actually make a solid according to the chart. Oxalate, again, +2, -2. These guys have big charges. They like each other. So you might not actually find them on the chart, but if you see a charge +2, -2 together and it's not listed, it's insoluble. So, and then the K and Cl, they don't like each other. They don't stick to each other. Putting down the complete equation here, this is 2 potassiums floating around, an oxalate floating around, calcium floating around, chlorine floating around. Over here, this guy's actually sticking together, so he's a solid. He has combined together, and it's not ionized anymore. It's not ionized into the solution. And then the K and the Cl. So what will cancel out? We see there's K's on both sides. Those guys will cancel out. The Ca and the C2O4, these guys here, they actually change. The calcium used to be aqueous, now it's in a solid compound. So he comes down to our net. The C2O4 used to be aqueous, now he's in our solid. He comes down to our net. The Cl is aqueous here, the Cl is a spectator. So here, the K and the Cl's, those are spectators. This one here looks like something we did with electrochemistry in first semester. So here we have a metal reacting with a solution. So we're taking a piece of magnesium metal, putting into an iron chloride solution. This comes down to the activity chart, like who likes electrons more for the metals. So iron with +3 charge is more electronegative than magnesium, and it will take magnesium's electrons. So iron chloride right here, aqueous, sorry I didn't put that up there, plus magnesium metal would result in the iron actually oxidizing the magnesium. And that's a word we haven't used for a long time, but this is just an oxidation reduction reaction. So the iron is going to basically take the magnesium's electrons. He's going to oxidize the magnesium, and the iron's going to be oxidizing iron's going to be the one that is, oh boy, it's been a long time since I talked about this too. So the iron itself, he is the one that is taking electrons. He is oxidizing the magnesium. He is the oxidizing agent. So magnesium is the reducing agent and himself is oxidized. So it's been about 3 or 4 months. So anyway, so we see our net reaction here then. The iron over here is floating around with his big positive charge. And then there's a chlorine with his negative charge. The magnesium here is solid. So he has no charge, he has his electrons. We see what happens is the iron is more electronegative and wants the electrons from the magnesium, and he takes them. So now the iron has magnesium's electrons. Magnesium has lost its electrons, and so our net reaction shows this, that, hey, really, this was just iron taking magnesium's electrons. This is the net ionic equation. So molecular equations, these just show the chemicals in their, when we put the molecule together, saying like, here's the salt, it's table salt, NaCl, write it all out. The ionic one is just putting everything in ion form, splitting them apart, taking the NaCl and separating it to saying, hey, we actually have positive Nas, we actually have positive Cl or negative Cls, let's separate them because that's what's going on. The net is just who did something, who changed. All right, I'm also going to have a little section here about the solubility chart because you'll be using some solubility logic to find out who some unknowns are possibly. So when you get to these stuff here, this would be an A-level topic. You basically have to figure out, based off how things react, who might it be? Think of this being like a toxicologist who is like trying to figure out, okay, well, what possibly might be the thing that hurt this person? All right, you're gonna try to find out what contaminant can we find? How can we find out what contaminant hurt this person? And so you might take some of the blood from the person and then mix it with a bunch of different things and see what does it react with to find out what's going on. All right, so we're just doing some logic with, based off how things react, who might it possibly be? All right, so we have some solution, we mix it with a bunch of things. Silver nitrate, beryllium nitrate, lead nitrate, potassium sulfate, and we find that we make a solid when we have silver nitrate and lead nitrate. What might be the anion in the solution? All right, so we're not gonna have enough information here to find out exactly what it is, but we're gonna be able to like just do this idea of like, let's logically think about who possibly might be the negative ion inside the solution, if there is one. So when we take the unknown and mix with AgNO3, we get a solid. So let's think about this. So we know that on our solubility chart, nitrate never makes a solid. Again, scroll down here, nitrate. All nitrates are soluble. That means that when we mix this thing together, we can be pretty sure that the nitrate is not the one reacting, all right? It's gonna have to be the Ag reacting, making a solid. So the question is, what does the Ag ion actually want to react with? Who would Ag react with? So we look at our chart down here. We see that Ag would react with halogens. Halogens normally are soluble, but Ag would make them make a solid. We see that Ag would also make acetate make a solid. We see that sulfates, oh wait, sulfates could be a possible option. I forgot to put that up there. Silver would react with sulfate. So put that up here too. All right, and then farther down too, we recognize that silver would also react with these guys here because these guys here, they react with most things anyway. So sulfides tend to be insoluble. Ag is an exception, so it could also be sulfide, maybe sulfides in there. All this really did for us was it eliminated, it just basically eliminated nitrate and nitrates and perchlorates. So pretty much this doesn't tell us a whole lot. The next one, we're told that it reacts with PbNO3 and makes a solid. So we got to find out, does PbNO3, does the lead react with this in the same manner? So looking at our chart, a couple of things that are different. There's only one here for us that's different. Acetate does not react with lead. Lead is not an exception. This means that lead would not react with acetate. So that means that it cannot be acetate in there, because if it was acetate in there, the acetate would have made no reaction with the lead. It would have stayed as something aqueous. So this eliminates acetate because acetate would have been no solid produced. All right, we see that it has no solid with beryllium. So let's see what else is found out here for us. So beryllium, for the sulfides, this tends to be insoluble, but beryllium is an exception. This means that beryllium, if it came in contact with sulfide, would actually stay dissolved. So the fact that this thing says no solids produced, this eliminates sulfide as an option. This doesn't help us at all here because K basically always is soluble. So we didn't expect anything to react to this. So we can't actually compare anything else to find out what's going on here. So basically all we have at this point is enough information to say it's probably a halogen or a carbonate or a phosphate. We know enough to know that it's not sulfides, and we know enough to know it's not acetate. All right, but those other ones are still possible options. All right, God's peace. Have a great day.